Hi, today I'd like to tell you about spontaneous parametric downconversion. So, spontaneous parametric downconversion is a technique to generate two entangled photons. And it was discovered around 1970, about 10 years after the discovery of the laser. And what it typically involves is shining a pump laser in at a certain energy, and then the photon in that pump laser will split into two photons with an energy that add to the energy of the original photon. So in this example, a 405 nanometer pump might split into two photons at 810 nanometers. So as a way to gain intuition for what's happening in this process, let's first look at the process of classical parametric amplification. So this is a situation in which we might have a weak signal at a certain frequency and want to amplify it by using a pump at a different frequency. Now, what this BBO crystal, or any crystal with some strong nonlinear susceptibility, has an ability to do is to transfer energy between modes at different frequencies. And so what will happen here is that we'll begin with just the signal beam at a certain frequency and the pump beam at a certain frequency, and the nonlinear crystal will generate energy or transfer energy between modes at the signal frequency and the idler frequency, where the idler frequency and the signal frequency both add to the pump frequency. And so overall, energy will be transferred from the pump beam into frequencies at the signal and idler frequency. Now, an important aspect of this is that if there's no signal beam to begin with, there's no amplification. And so this spontaneous parametric downconversion is actually not allowed at all classically. And quantum mechanically, it's an extremely weak process, which is one of its limitations, but it's also why we can generate single photons with this process. So there's a great review paper by Christophe Coteau that goes into a quantum mechanical model for spontaneous parametric downconversion. And what we're interested in this case is a quantum state that contains a certain occupation of photons at the signal mode, the idler mode, and the pump mode. And what's going to happen is that the signal and idler mode photons are what will be entangled. So what's important for our purposes for generating entanglement in the polarization is that the signal mode and the idler mode are at opposite polarizations. Now, we can write down a Hamiltonian for this system in terms of creation and annihilation operators. So for example, this term would be the annihilation of a pump photon and the generation of a idler and signal photon. So these sorts of terms are what represent the process of the annihilation of the pump photon generating the signal and idler photons. Okay, so how would this work in an actual experimental setup? Let's imagine that we have some pump photon coming in, and it splits into an idler and signal photon, where the idler and signal satisfy these energy and momentum conservation relations. So we'll have these two photons, but we don't know which is the idler photon at the horizontal polarization and which is the signal photon at the vertical polarization. Now, let's imagine that we have a detector somewhere over here. What we'll find is that the probability to measure a photon with momentum along this line spreads out in a cone, like as illustrated. And similarly for this other momentum photon. So if we look at these 2 points at the intersection of the cones, where we could have detected either photon, then the probability to get a horizontal or vertical polarization at these 2 points is entangled. So this is a very famous picture in the literature of spontaneous parametric downconversion. We basically have the emission from a BBO crystal in these two overlapping cone shapes. And once again, we can mathematically represent the state between these 2 points as entangled and the horizontal and vertical polarization. So that's basically how it's done. A couple challenges to mention are that we need something called phase matching, which is equivalent to this momentum conservation relationship. But this is sort of challenging to actually do in practice because the k-vector of the material is dictated by the index of refraction at that particular frequency. So we have to choose the correct crystal and use the correct orientation in order to get the right phase matching. Another thing is that we will typically do a coincidence measurement. So we're looking for photons to arrive at the detector at the same time in order to get the entangled state. And so if there's any unwanted delay between this photon and that photon, we might not be able to see them at the same time. So we'll have to get some sort of compensating optics. And then finally, one of the challenges of this technique is that it's a very weak effect, so you might not get very many photon counts per second. One of the ways to address this is to simply increase the pump power. However, this comes with an intrinsic trade-off, which is that as you increase the pump power, not only a single photon pair, but actual multi-photon pairs become more likely to be emitted from the crystal. And if you're just doing an experiment that relies on a single photon pair, this will destroy your experiment. So there's sort of this intrinsic trade-off. Okay, so now that we have a feel for what spontaneous parametric downconversion is, one of the key applications is in quantum communication because it's sort of this fundamental way to generate entangled photon pairs. One of the cool results that I want to highlight is that people were able to actually generate these photon pairs at telecom wavelength, so that's good for transmission through a fiber, for example. And then another interesting application is in quantum teleportation, which has also been experimentally achieved. So in this case, Alice has a state that she wants to send to Bob or teleport to Bob, and the way that she does it is by generating an entangled photon pair, sending one of those entangled photons to Bob, and then doing a measurement on her state combined with her side of the pair, and then Bob can recreate her original state. So this was done to transfer the state of a photon into the state of a solid-state qubit, which is pretty cool. And it's also something under active development and improvement. So another application is in quantum computing. There have been various proposals for optical quantum computers, and an experimental result that I particularly want to highlight is the demonstration of a C-NOT gate between two photons. So spontaneous parametric downconversion was the way that these experimenters generated their entangled photon pair, and then they applied these various wave plates and beam splitters in order to flip the state of the test bit based on the state of the control qubit. So in terms of the state of the art on optical quantum computing, there have been some papers which try to use spontaneous parametric downconversion to increase the number of photon pairs that you can work with. So this is an example where they were able to work with 10 photon pairs at once. The way that they did it was by using these individual photon generation events, similar to the technique that I discussed earlier, and then combining multiple sources at once in order to get multiple photon pairs to use in the quantum computation. So I think that people have been getting better and better at generating more photon pairs, but ultimately this is limited by the ability to reliably and quickly generate the individual photon pairs from the spontaneous parametric downconversion. So before moving on to the state-of-the-art techniques, I want to mention one historical application, which is that the SPDC was the first way that people were able to generate entangled photon pairs and test Bell's inequalities. So historically, this effect also played a role in testing the foundations of quantum mechanics. But today, I think a lot of the current research is aimed at increasing the strength of this effect. So, for example, we might want to electronically pump the system as opposed to optically pump the system. So that's something that people have been able to achieve. And then also people have played with metamaterials in order to enhance the strength of the effect, and also place the material inside cavities to enhance the strength of the effect. And the other push is to integrate these single photons into photonic structures in order to do more information processing with them. So there's been some efforts to generate these in thin films of silicon nitride, for example, which is interesting because silicon nitride typically would not have this strong nonlinear optical effect that, for example, a BBO crystal might have. So there's some interesting engineering challenges in combining the I guess, good propagation characteristics of many photonic materials with the nonlinear generation capability of typical crystals. And then, yeah, another thing is actually generating these single photons already inside optical fibers. So that just reduces the need to fiber couple. So that's another direction that people are going. Yeah, so in conclusion, spontaneous parametric downconversion is a leading technique to generate entangled photons. For generating single photons, other techniques such as emission from atoms or atomic dots are more efficient. However, SPDC does have a use case for heralded single photon generation, in which one of the photons from SPDC will hit a detector first and alert the experimenter about the arrival of the next photon. As far as other techniques for generating entangled photons, there are cascade techniques with atoms or quantum dots, where an electronic energy level will be de-excited twice and emit two photons. These are preferable in some cases because they can be more electronically controlled. However, SPDC is a leading technique to generate large numbers of entangled photon pairs. As far as improvement in the future, a lot of the work is going into designing materials that have a stronger generation coefficient for SPDC, and also materials that either natively generate the photons inside a photonic structure or easily couple to a photonic structure on the chip. Another interesting example for a future direction is entangling multiple degrees of freedom. So for example, the polarization and the orbital degree of freedom at once. And then I think a fundamental trade-off is that we want to generate many photon pairs at once for quantum computation, for example, but it's difficult to do so in a controlled way because this process does give random photon emission, and also increasing the pump power will increase the number of multi-photon emission accidents. So with that, thank you for your attention.